California, or you're in Europe now?
I am in Portugal.
In Portugal, okay. Enjoy.
Well,
mathematics and food, both.
okay. I try.
Okay, so it's 12. It's my great pleasure to introduce Maria Fernanda Botello from University of Memphis. She is going to talk about contractive projection and lifting of operators on Banach spaces. Maria, please.
Thank you very much, Javad. I'm most grateful for this opportunity to speak in this program. Has been a great series of lectures and mini courses throughout a long time, and so I'm very honored to be invited and participate in this program. Here is the title of my talk: Contractive Projections and Lifting of Operators and Banach Spaces, and this is based on joint work with Monica, a graduate student at the University of Memphis, Richard Fleming, and TSS RK Rao. So let me start by describing the setting we are working in. Let X be a Banach space and J is a closed subspace of X. Then pi is the quotient operator from X into the quotient of X by J. Then we say that the identity map or operator on the quotient space X by J has a lift if and only if there exists an operator denoted by identity tilde from X from the quotient X by J into X, such that these two conditions hold. Has the same norm as the identity, and this operator followed by the quotient map gives us back the identity operator. Here is the representation in a diagram of what I just said. So I have the Banach space X, a subspace, and therefore the quotient space. Here is the projection map, and I have the entity. So we say that this operator has a lift, provided I can find an operator from the quotient to X that makes this diagram commutative, and also the norm is preserved. Here is an interesting fact. If we assume that the identity has a lift in the sense I just described, then for every Banach space Y and the bounded operator S from Y into the quotient, there exists a norm-preserving lift in a similar sense I just described of the operator S. And here is what this means, that this new operator S tilde followed by the quotient map gives us S, while the norm is preserved. Here is how this is defined. This new operator is defined. We have S from Y into the quotient by J. This is S. And we know that the lift of the identity exists, and that lift is denoted this way. And that takes us back to X. Then we define S tilde as this composition. And it turns out that this satisfies the conditions listed above. First, if we follow this operator by pi, because this composition here is the identity, it gives us back S. And more, if we, concerning the norm of the operator, because the norm of this lift is equal to the norm of the identity, so less or equal than 1, that's clear that the norm of this operator is less or equal than the norm of S. And also, because S is equal to this, and pi has norm less or equal than 1, then we have the reverse inequality, which explains this equality right there. So if the identity has a lift, then there is lifts in this very same sense for any other bounded operator from any other Banach space into the quotient. Okay, so let's see an example of where this happens. Let's take X to be a Hilbert space and J to be a closed subspace. Then it's easy to see that if we take a closed subspace and look at the orthogonal complement, that decomposes H. So I have H equal to this direct sum. And then if the quotient space of H by K can be identified with the orthogonal complement, and therefore the identity here takes an element in the orthogonal complement back to itself, and the projection is, in fact, in this case, just a projection. If I take a pair or look at X comma Y, it takes us back to Y. And here we just the lift, it's just an inclusion. So in this case, we have here an example of a pair of Banach spaces, in this case, Hilbert space, such that H Hilbert space and the closed subspace, and the pair has the property that I just mentioned. But here is an example where this does not happen. Let's assume I have X to be R, three-dimensional space, endowed with the max norm. And let's take J to be the one-dimensional subspace spanned by 1, 1, 1. So I'm gonna try to briefly explain why there is no lift of the identity on the quotient. Okay, here is some steps. First, it's fairly easy to accept that the quotient of X by J is a two-dimensional space, R squared, endowed with this norm that is defined in such a way that makes this map an isometric isomorphism. So takes an element in the quotient space, so X, Y, comma, Z plus J. J is the subspace, into X minus Z over 2, Y minus Z over 2. And then a calculation, we can see that if we endow R squared with this norm, this phi is an isometric isomorphism. So instead of looking at the quotient, I can just look at this R squared to carry on my argument. Now, if we consider the identity map operator on X tilde is R squared, so XY goes to XY, and I look for a lift of such a map, then the lift must be, any lift must be of the form 2x plus h, 2y plus h, h being linear in X and Y. So this is, it's easy to check that indeed that projects down when we compose with the phi to the identity, because we just subtract this third component from this, say, first component, divide by 2 gives me X. The same thing for the second and the third gives us Y. So indeed, this is a lift. So among these possibilities, I need to find the one that has equal norm. In this, we have that, so if we follow pi, or between quotes, pi with this identification of the quotient with this R2, so this plays a role on that, we can check that indeed it projects down to the identity. So the first part of the definition holds true. I just need to make sure that among all these possibilities, I have one that preserves the norm of the, so has one in this case. So then we realized that if we look at identity tilde of 1, 0, that should be equal to this for some h to be defined. But because I wanted to have norm 1, then from this coordinate right here, that tells us that absolute value of h10 is less or equal than 1. But then h, if I'm working with the real scalars, should be between -1 and 1. And therefore, if it's greater than -1, this first coordinate tells us that cannot be, because that value 2 plus something greater than -1 is greater than 1, and therefore the norm of such an operator would not be 1. So now similar argument applies to the other, to the companion vector 0, 1, and similar for the similar argument, we conclude that these two, they must be equal to -1. But then the linearity of h tells us that the sum H of 1, 1 must be -2. And then if we look at the identity tilde, my candidate for the lift, at the point at the vector 1, 1, that is 0, 0 minus 2, and therefore cannot be, the norm cannot be 1, it's at least 2. So this explains why there is no lift of the identity for this case. Though I have a dimension 1 subspace, and it's just a 3-dimensional space that I'm working with. Now I'm gonna write down the definition of the quotient lifting property. We have a Banach space, we have a closed subspace, and then the pair xj has the quotient lifting property if and only if the identity has a norm preserving lift in the sense we just described. So the norm is preserved, and this lift followed by the quotient operator gives us back the identity. Okay. So as we saw before, this is equivalent to say that for every Banach space Y and the banded operator from Y into the quotient, there is a lift. There is an S tilde from Y to X such that these two conditions hold. I have shown you how to define this S tilde, provided this is true, the identity has a lift, and clearly the other way is just a particular case of this statement by just taking Y to be a quotient space and S to be the identity. So if this holds, so that holds clearly. So that those two conditions are equivalent. And from here, we have that if I start with a pair with the quotient lifting property, then if I define an operator, so we have the identity tilde is the lift of the identity. So we have identity tilde goes from the quotient to X, identity tilde, and then pi takes us back the quotient. This pi is the quotient map. Then if we follow pi and then this identity tilde, this operator is a contraction and it's a projection. And it's easy to see that it's a projection. We just write down, just check that it's idempotent, composed with itself. And we see that this gives us identity, so we get back to P. That's a projection. And it's interesting to point out, and fairly easy to see, that the kernel of this projection is J. So this property is directly related to kernels of contractive projections. There's a lot done in the literature for ranges of contractive projections, but we have not found that much on the kernels of contractive projections. So in this case, we can say one step further that xj has this property if and only if j is the kernel of a contractive projection. So let me try to justify this in a few steps. The proof is just a couple of lines. So if I start with a pair that has the quotient lifting property, that's pretty clear that j is contained in this because j is the kernel of pi. So now if we start with the x, that's for which this is true, so in other words, x is in the kernel of this composition, then if we apply pi, we have that pi of this of 0 is j, is the concept 0 plus j. But on the other hand, this composition here is the identity. So this becomes pi of x. And pi of x, that is j, as we see up here, it's also x plus j, so therefore x must be in j. So that tells us that if x is in the kernel, gives us the reverse inclusion, and therefore equality. No more, if I start with j, the kernel of a contractive projection, then it is easy to see that I define, so to go in the opposite direction, I need to prove that x comma j has the quotient lifting property, or the identity on the quotient has a lift. So let's try to define the lift of such an operator, x plus kernel of p, and that's what's natural to think about is assign it to be p of x. So the identity tilde in this case goes from xj to x, such that when it compose with the quotient map, yields here the identity. So in this case, we consider this operator to be given this way, the P of X, the projection P that we start with, whose kernel is J, and the kernel is J. So that's what appears in here in this quotient space. But then it's easy to see that if we compose with pi of this, so we have P of X plus the kernel. That's what pi does to this vector right there. And it's also this is equal to X plus the kernel because X minus PX is in the kernel of P. So if we apply P and P is idempotent, that yields 0 when applied to X minus P of X. Also, now towards the norm, that the norm is preserved, we just have to realize that the norm of Px is equal to the norm of P of X minus K, K coming from the kernel of P that we also represent, set it equal to J, to the subspace J. And then because P is a contraction, this is less or equal than that, and then the norm of X minus K, and therefore, since K is arbitrary in the kernel, that tells us that the norm of P of X is less or equal than this, and therefore the norm of the identity tilde is less or equal than 1, unless it's trivial, and that implies that the identity, so J is equal X, it's going to be 1. Okay, so now from what we just saw, if Xj has the quotient lifting property, then J is the kernel of a contractive projection. So therefore is the range of a bounded projection, namely identity the complementary projection, identity minus P. If I call P the projection that yields the J, whose kernel is J. Then it's easy to define or look in the literature for pairs that do not have the quotient lifting property. So one of which is this one. It's well known that C0, it's not complemented in L infinity. This is a classical result from Phillips. It goes back to 1940. And for that reason, it cannot have the quotient lifting property. Now, what I'm about to talk about here is that it is a straightforward application of results from J. Johnson back in 1979, that the following two statements. First, here is the preamble. If I have E and F Banach spaces, and del EF denotes just the bounded operators from E into F, and K of EF, the compact operators from E into F. And if F contains a complemented subspace isomorphic to C0, then this pair does not have the quotient lifting property. And the reason is, it was shown by Johnson that the compact operators in this case, under this assumption, it's not complemented in the bounded operators from E to F. So for that reason, we cannot have the quotient lifting property. Or just to review what we said, the identity on the quotient space has no lift. More, if we have F that with the approximation property, that's the range space, has the approximation property, then the dual space of the bounded operators and the annihilator of the compact operators, this pair has the quotient lifting property. And the reason is, again, is a straightforward application from a theorem by Johnson, which says that in this, under this assumption, this space is the kernel of a contractive projection on the dual of the bounded operators from E to F. So for that reason, then the pair has the quotient lifting property. Here is a remark, which is that led us to investigate a question that I'm about to explain. And here is the following. Let's consider this simple example, R plus R with the L1 norm, so one norm, and J is the span of this vector, 1 minus 1. So to decide on the the quotient lifting property for this pair, we have to decide on if there exists a lift of the identity operator on the quotient of the space by J being this one-dimensional space. So I'm talking here about one-dimensional space, identified one-dimensional space, and again, the quotient. And it's easy to see, I think, that a lift of identity is this one. So if we consider x, y plus j coset in the quotient space and identify to it x plus y comma 0, and I think it's fairly straightforward that this is well defined. And because of the way j is defined, has vectors of the form t minus t. And this line here is just to explain that indeed the norm of such an operator is 1, so it's preserved, it preserves the norm of the identity. And then we realize that in this case, if we have, instead of considering x plus y on the first component, we put it on the second component, we have another lift. So the question that came up was, when do we have a unique lift of the identity? And of course, this is still the answer to this question is still in its infancy, but I just want to share here a result that came from results in the book on M ideals by Adamar, Wormer, and Wormer, and they mention that the result by Sullivan that justifies this statement that I wrote here. But before that, one claim is that one observation is that for the identity on the quotient space to have a unique norm-preserving lift is equivalent to say that there is a unique projection, contractive projection, whose kernel is J. So, and a result by Sullivan says that second closed subspaces of a very smooth Banach space, there is at most one projection on the dual space with range J. So therefore that allows us to take the adjoint, and then the annihilator of the range becomes the kernel. So that's the idea. But so therefore here I have the statement, if X is very smooth Banach space, and J is a reflex subspace, and we'll always have this, so it's finite dimensional, for example, then X star, the dual of X, and the annihilator of J, if that has the quotient lifting property, then the annihilator of J is the kernel of a unique contractive projection. And just to review some definitions of what very smooth is, if we have a smooth space, Banach space, then for every X in the unit sphere, there is a unique functional in the dual space that attains its norm at X. So it's a norm 1 functional that attains its norm at the point X. And if this is unique, then we say that X is smooth. To be very smooth, this map that takes X into tau X is weak to norm to weak continuous. It's if it is smooth, it's known to be norm to weak stack continuous. So, but if it's to weak continuous, then we have what's called very smooth. And it's interesting to mention that in embedded spaces can be renormed to be very smooth. And a norm embedded space is a space that it's an M ideal in its bidual. So, this is a class, quite important class of spaces that are M ideals on their double duals, M double star. And here, just to add one more theorem along those lines, is a characterization of those subspaces of L1 that yield that have the quotient lifting property. So if we start with a Y, a subspace of C0 on gamma is where C0 is defined, not necessarily a sequence space, could be a function space. And then the dual space of C0 is L1. And here, this pair is the annihilator of Y, has the quotient lifting property if and only if y is isometric to L infinity, finite dimensional, for some positive integer n, or C0 of some gamma prime, or it is isometric to C0 of some, so here we have a sequence space, because gamma prime is a discrete set. So the proof for this statement relies on 2 points. First one is that C0 is an n embedded space. So it's an M ideal and it's bidual. And the other is the result by TSS Rao from 2018 that basically tells us if this is the range of a norm one projection, if and only if this statement occurs. So this is almost a two-line observation and how to justify that result. Here, a remark, and I apologize, I don't have many examples from spaces of analytic functions, but we just heard about block spaces. So here is an observation involving block spaces. Block space, just for this, I just took here the definition to review. So you have analytic functions on the open disk to see into the complex numbers. Of course, here could be also a vector space. And such that, a Banach space instead of C. And here we have the condition that characterizes those functions that belong to the block space, is that the supremum over the Z's inside the open disk of this quantity is bounded. So this exists, supremum is less than infinity. And then the norm considered in this space is absolute value of f of 0, the value of the function at 0, plus this supremum. And we have the little block space, which basically says that the limit as, this quantity decays to 0 as we approach the boundary. And it's known that the little block space is an M ideal space, an M embedded space, is an M ideal in the bidual of the little block space, which is known to be the block space. So, but on the other hand, it is not complemented. So we have that this pair does not have this property, the quotient lifting property, though it's an M embedded space. Now I need to review a couple of definitions. So if I have a subspace of Banach space X, then we define the metric projection on J as being the set of, given an X in the Banach space, in X, we associate the set of all J's in J such that the distance from X to J is equal to this norm of X minus J. So, of course, it's possible that for some values, for some vectors in X, this set is empty. It's possible. It's also possible that it has more than one point. So this leads to some definitions, the first of which is that J is, what does it mean to say that J is proximinal in X? This is basically says that this set is never empty. So for every X in X, there exists a set of points in J that are at smallest distance from X. Then based on this, and this metric projection here is a set value function if I consider proximinal subspaces of X. Actually, this is also appropriate for just subsets of X. But if we have a set value function and for each X, the set is non-empty, it's possible to select a point from each set. So it's possible to define a map. So, well, using a choice. So I choose, so define a function Q that Q of X belongs to this set of the closest elements in J to X. So when such a choice is linear, then we say that we have a linear selection. So all these functions, so defined, I call selections of the metric projection. And this last one, I'm not going to talk much about it. It's just for completeness of the definitions, is what does it mean when J is Chebyshev? Is that says that is proximal and all these sets reduced to a single point. So in that case, we say that J is Chebyshev. Now I want to show a few results that are necessary, sufficient conditions and some necessary and sufficient conditions for a pair to have the quotient lifting property. The first one is, if we have the pair with this property, then J is proximal in X. So that means that the metric projection is actually a set valued function, and for each X, the set associated with is non-empty. More, if Xj, this pair, has the quotient lifting property, then P sub j has a linear selection. So you can choose a function using the axiom of choice from each set, choosing a function, a point that is at the closest distance, but I can choose one such that is linear. And we already saw that J is a complemented subspace. In that case, if it's linear, it's going to be bounded, and therefore J is complemented, right? J is the range of such a projection. More, if Xj has the quotient lifting property, is equivalent to say that J is the kernel of a contractive projection. We have seen this one before in the previous slides. But lastly, if J is the proximal subspace of X, P sub J has a linear selection, then the pair has the quotient lifting property. So if we restrict ourselves to proximal subspaces, then the existence of a linear selection is equivalent to this condition of the quotient lifting property, or if you want, that the identity on the quotient has a lift. So it is a result in Singer's book that X is a reflexive Banach space if and only if every closed subspace is proximal. So proximality of subspaces characterize the reflexive Banach spaces. Then with that, it's clear that if we start with a non-reflexive Banach space, then it contains always some J that it's not proximal, and therefore contains X has always a pair that does not satisfy the property. And but it's also a fact that if for every X contains a subspace such that the pair Xj has the quotient lifting property. And for that, we just consider a one-dimensional subspace. And one-dimensional subspaces are ranges of contractive projection, of contractive projections. And if we look at the kernel of that projection, that kernel, that subspace defines with X a pair with the quotient lifting property. So now, in one of my talks, when I was referring and mentioning that J being proximal is necessary for the pair to have the quotient lifting property, TSS asked the question, how about other notions of proximinality? And he mentioned this simultaneous proximinality, which is a very natural way, because natural one, and that says the following: if you look, if I have X represented this way, I have 0, I have a subspace J, and proximal means that for every X in X, I find here in J a point that a vector that it's at closest distance. So simultaneous proximinality involves a notion of proximal, but instead of considering just one point, considers several points. And actually here I restrict it to finite subsets of X, and but it's also true for bounded subsets of X, and a similar definition is considered, has been considered. So here is the definition. We say that the finite subset of X, actually for every finite subset of X, A, there exists a point in J such that this infimum is equal, is actually attained by, that this is the maximum of all the distances from capital A, that it's my set to J. So it's actually attained at some point in J. So in other words, there is we can define a radius of a ball that centered at J naught, and with that radius contains the finite set A in this case. So and the question was, does the quotient lifting property implies such a notion of proximinality? And the answer is yes. And here is just a quick outline of how that goes. The idea here, the proof is just for two simultaneous proximinal. Instead of considering A to be finite, I just consider A reduced to 2 points, but the same proof extends. The trick is to consider this new space, X plus X endowed with the infinite norm or max norm. And the diagonal of J, we mean just the closed subspaces of defined this way. Then we are gonna, given this operator that takes X comma Y in here plus diagonal, this is a coset in the quotient space, associates X plus J. And of course, this is well defined because the way the diagonal of J is considered is just all the pair J from J in J. And this operator has a lift because, you know, I'm assuming that Xj, this pair has the quotient lifting property, and therefore, for every operator from a Banach space Y, this one, into the quotient has a lift. So does this one, and I denote such a lift by F tilde. The same thing for F2, and we denote the lift by F2 tilde. Then, if we consider to prove that the pair, this pair has the quotient lifting property, we just need to show that the identity on the quotient space has a lift. And then the quotient, the identity on this quotient space, the lift of such an operator is defined as follows: identity tilde of X comma Y plus the diagonal is F tilde 1 of XY plus and comma F tilde 2 plus the diagonal. So I go back to, so I go from here to here. Sorry, plus diagonal, yes. That's the lift of the identity. And then this implies that this pair has the quotient lifting property, and which implies that the diagonal of J is proximinal in here. So there exists a point J that does the trick for the simultaneously proximinality condition that we are looking for. So this is the outline of the justification for this statement. So now we have, again, a condition that we have seen before. If P is a contractive projection on X, then this pair has the quotient lifting property, this being the kernel of the projection P. Talked about. So it's clear that if we start with a bicontractive projection, then we have two pairs that are defined from P that both have the quotient lifting property. This is the one above because P is contractive, and this one because this is the kernel of the complementary projection identity minus P, so also has the quotient lifting property. Now, bicontractive projections are quite well studied, and we have here examples of three kinds. We have M projections that are defined in this way. Norm of X is the maximum of norm of Px, and the norm of the complementary projection at X. Or L projections, also bicontractive, and norm of X is the norm of Px plus the norm of identity minus P at X. Then you have another class by circular projection and generalized by circular projections. And here is the definition of the generalized by circular projection. And this is due to Fojna, Ilizhevich, and Shiquan Li back in 2007. We have that X is a Banach space. A projection P on X is said to be a generalized by circular projection, provided this is true. The following statement holds: P plus lambda, and this is identity minus P, and is a linear isometry for some lambda of modulus 1. So lambda is modulus 1, but it's not 1. And in this case, different from 1. In this case, it's clear that this, if it's a linear isometry, is going to be a surjective isometry. And if this condition holds for every lambda, then we say that we have bicircular projections. And now an observation due to my colleague and friend and collaborator, Jamieson, 2008. He realized that when this condition holds for every lambda, then for all lambda of modulus 1, this is equivalent to say that P is Hermitian. Okay. So that being said, I'm going to import or recall here a result due to Diana in 2010. She characterizes the generalized by circular projections on JB star triples. And so here is the statement. If X is a JB star triple and P is a linear projection that satisfies the condition that I just presented in the definition for generalized by-circular projection, then P is of one of the following forms: either is Hermitian, is Hermitian, or P is the average of an identity with an isometric reflection. And this description of these projections have been studied in several settings, and this observation is true in many different spaces. Spaces of analytic functions, Hardy spaces, and block spaces, Zygmunt spaces, a lot appears to have the same form. So if, of course, such projections are bicontractive. So T is an isometry, identity, the norm of P is 1 or less or equal than 1. And identity minus P is 1/2 identity minus T again. So it's of norm 1, unless it's a zero projection. So we don't want to consider that. So then here is an example that follows from this. If I take X to be the continuous functions on -1, 1, and this is a JB star triple, is a commutative C-star algebra. Okay. And if we consider T to be isometric reflection, for example, f of minus T, then if we write down P to be 1/2, so at f of f plus TF, then we realize that the range of this projection P is the set of all of the space of all even functions, and the kernel is the space of all odd functions. So we have a pair defined from this space and from the form of the surjective isometries, two natural pairs that have the quotient lifting property. Now, I'm going to talk about a particular case, and this is a situation that Hilbert spaces satisfy, and it's the following. Suppose Hilbert spaces has the following property: for every closed subspace J, the pair has the quotient lifting property. You have seen that before. So this leads to a definition that we call the total quotient lifting property. And actually we start with complete quotient lifting property, but then we consider the compact quotient lifting property, where some of this study does not apply because the identity is not necessarily compact. So we just consider lift of compact operators. So we changed it to total. So where every closed subspace J, the pair X comma J has the quotient lifting property. So the question is, which spaces possess this property, the total quotient lifting property? Of course, Hilbert spaces do. We have seen that. But we have this space, for example, R direct sum with R with max norm, that also has the total quotient lifting property. And this is very simple to see because subspace of this are one-dimensional and also one codimensional, and those pairs have the quotient lifting property. So, and this is not a Hilbert space, is isomorphic to a Hilbert space, but not a Hilbert space. It is also clear that if this property holds, then J is complemented in X. So this situation tells us that every closed subspace is complemented, and it is a classical result due to Lindenstrauss and Zafriri that X is isomorphic to a Hilbert space. But what it turns out to be is that if we consider a dimension of the Banach space X greater than 2, then in fact, we have, this could be used to characterize the Hilbert space. We can have only a Hilbert space. And this is the outline of the justification for this statement. And first, we have that we know that every closed subspace of X is proximinal. That was one, because proximinality is a sufficient condition for the property to hold. Hence, X is reflexive. This is a result that appears in Singer's book, so proximinality of every subspace is a characterization for reflexivity. Then if we start with W, a closed subspace of X star, which is the dual space of X, then J, if I set J to be the annihilator of W, this is a closed subspace of the double dual of X, which is X, because X is reflexive. Then this pair has the quotient lifting property because I'm assuming that X has the total quotient lifting property. And therefore, J is the kernel of a contractive projection P. Then if we look at the dual or a joint of P, the range of it is the annihilator of J because it's the annihilator of the kernel of the projection P. But since X is reflexive, we have that annihilator of the annihilator. This is J here. Annihilator of the annihilator takes us back to W. W is closed subspace. Since every space in X star is the range of a contractive projection, then we use a result due to James back in 1947 that says that the space X star is isometrically isomorphic to a Hilbert space. But if the dual space is a Hilbert space, so is X. And so this is the outline of the proof that indeed, if we have the total quotient lifting property, then X is a Hilbert space. And we all have seen that if X is a Hilbert space, then this property holds. So here is the references that I based this talk on. This is joint work with Monica and Fleming, Richard Fleming, and also TSS RK Rao. And I'm most thankful for your attention. And so I think I'm okay. 2 minutes before time. Okay.
Sure, sure. Thanks a lot, Marielle. Let's thank the speaker first.
Thank you.
Any question or comments for Marielle?
I hope the semi-groups would bring some insight to this. I apologize not to have much semi-groups in it, but
hopefully it's in the same direction.
Yes, hopefully. Thank you very much for your attention again.
Okay, let's thank Maria again.